So then we're going to move on. We're in chapter 5 now. Last big hurrah. 5.1. We're going to talk about, I think it was integrals and antiderivatives, but I think I said antiderivatives and integrals. Let's write as integrals and antiderivatives, because the integral is what I'm going to talk about first. This is usually written as one word. It's not necessarily hyphenated. So what we're going to do today, I don't know if you recall, but in the beginning, like in lecture 1 or 2, I mentioned to you the two big problems that calculus was kind of meant to solve. And what we have now is just everything that erupted from being able to solve these two problems. We could do a lot of other things. So we're going to attack the second problem. And this is the area problem. So remember I told you about calculus was about solving two kinds of problems. There was the rate problem, figuring out how fast something goes. And our answer to that was the derivative. It was a very sophisticated way. We could model something with a function, and that function had nice enough properties. We could find a derivative, and we could describe how fast that thing was moving. And just by figuring that out, we could figure out a lot of other things, right? We could do optimization, related rates. We can figure out where maximums are, where minimums are, when something's increasing and decreasing. There was a lot of stuff. There was a lot of nice things that we could do that resulted from us solving that problem. Similarly, we're going to attack the area problem, and there are going to be a bunch of nice things that fall out of this. We're not going to touch them because it's really Calc 2 that really deals with this. When if you want to study this a lot deeper, Calc 2 and 3 goes into that. It's a lot bigger than the area of derivatives are, but it's one of the main problems that we're here to solve. And so it's the area problem, and basically that's figuring out how much space something takes up. Okay, so you can imagine. If you were a farmer or something and you had some plot of land, you'd want to know exactly how much land you own, right? So the area of that, how would you know what that is, right? And many things kind of depend on this. For example, if the government is charging property taxes and they're claiming you have this much land, but you think you don't have that much land, you need to prove it somehow. How do you actually measure an area of some sort of irregular figure? Right? That's the idea. Ideas, because I think you've actually tackled this problem before in like algebra class. What did you usually do if you had to have this weird thing and you were trying to figure out how much space or the area? Yeah?
You put small shapes.
Put small shapes inside it, exactly, that you do know how to find the area. So one thing you might have done, more than likely, is you might have put this thing on a grid. Right? Basically fill it with rectangles or something else that you know how to find the area of. You can find the area of each individual pieces. The things that are kind of don't fill up one of the entire things that you know how to find the area, you kind of approximate, so you can kind of say, oh, this is about half of the rectangle here, and so we can assume that's half the area. And if you want to get even better, you would dissect it even further. Right? So you get even a smaller units of measurement, you get to fill in the little crevices, right? We're going to do the same idea here when attacking the area problem. The difference is we're going to come at it from a different angle, from a more sophisticated angle. So let's say I think of this shape as being connected by two curves. There's a top curve, and there's a bottom curve. Now, one way I can think about the area is if I can figure out the area under the top curve, and then figure out the area under the bottom curve, I can subtract them, and that would be the area of the figure, right? And so now the question becomes, how do we find the area under the curve? Right? So if I have a random curve on some interval a and b, how do we find this area? Right? So that's going to be the goal. That's the question we're going to answer today. And the answer is not as difficult as you might think, although the theory that we build around it can get quite sophisticated. But the answer is going to be pretty much similar to this. We're going to use a bunch of shapes that we know how to find the area to fill in the insides of that thing, and then we're going to add them all up. is essentially what it's going to be. And this thing is called integration. That's what integration is, and the integrals are the tools that we can use to complete integration. So the idea here is use rectangles under the curve. And approximate the area under the curve with the sum of the areas of the rectangle. Right, so that's the idea. We have some curve. We want to find the area under that curve from A to B. So what we do is we're going to split this guy up into several subintervals, they call it. You split the interval A, B into subintervals. On those intervals, you make rectangles. And basically, we add up the areas of those rectangles, and we use that as an approximation for the area under the curve. Okay? There are many ways to do this. We'll discuss three. So there are three methodologies under which I would expect you to be able to use this, and I will describe to you how you want to use them. There's a right-hand rule, not to be confused with the right-hand rule from physics. There's a left-hand rule. And there's a midpoint. So these are the three ways we're going to fill in rectangles. So let me sort of illustrate those to you. So one, in the right-hand way of doing things, what we do is we have this curve, and I'm just going to make a random curve here. I care about finding the interval from the area from A to B. What I do is I split the interval into a bunch of pieces, and on each of these pieces I'm going to erect a rectangle. But how I make those rectangles is I let the right side of each interval touch the curve, and that determines the height of the rectangle. So I look at this interval, I go to the right side, touch the curve, and I make that the height. Right side, touch the curve, make that the height. Right side, touch the curve, that's the height. Right side, touch the curve, that's the height. So this is approximating the area using the right-hand rule, right? Basically, you cut up the things into a bunch of subintervals, put rectangles on those guys. The height of the rectangle is determined by the right side of the interval. As you can imagine, the left is pretty much the same, except you go from the left side, right? So I can have this curve here. Here's A, here's B. Again, I'm going to dissect this guy dissect the interval A, B into a bunch of, they're called sub-intervals. And on each interval, I'm going to let the left side touch the curve. So the left side goes up, that determines the height. The left side goes up, that determines the height. The left side goes up, touch the curve, that determines the height. The left side goes up, touch the curve, that determines the height. Midpoint. I think we're getting the idea here. So in the case of the midpoint, we cut things into a bunch of rectangles. We cut the interval into a bunch of subintervals, but now we take the midpoint of the subintervals to determine the height. So here's A, here's B. I can dissect this into a bunch of subintervals. Sure, these form intervals on their own, but what I do is I then go in and I take the middle value, and I move that up, and I take that as the height. The middle value, that's the height of my rectangle. Take the middle value, that's the height of my rectangle. Middle value, that's the height of my rectangle. So then I get sort of this thing going on. So three main ways to do it. You'll notice that in this case, Meaning, don't assume that what I'm saying now applies to all cases, but you'll see that in this case, this guy gives you an overestimate for the area. You'll notice that the rectangles cover all the area under the curve, plus they give you a little more. Right? So the answer you'll get by adding up these rectangles actually gives you something that's bigger than the actual answer. While this one actually gives you an underestimate. You can clearly see that the rectangles, even if I add up all the areas, there are little pockets of area under the curve that I didn't get. Right? When you look at the midpoint, you'll notice it kind of wants to attack one or the other. I mean, it gives you a little overestimate here, but then it compensates by making a little underestimate there. So it's just an estimate. You can't be sure in a priori whether it's an over or underestimate. You kind of have to do some more calculations. But that's sort of the idea. And different curves can have different things for each of these methods. Sometimes this can give you an underestimate, sometimes this can give you an overestimate. You never know, it depends on the shape of the curve and what it's doing. But these are the three main modalities that we're going to be working in here. And so it's just a way to estimate the area under the curve. Now you can see, in this case, probably this guy is going to be the more accurate, but no matter which case you want to use, we want to be the most accurate we can be. And so the idea is we're going to further the technique by saying, well, if I wanted to not have as much overestimate or fill in all these gaps, what could I do? Same thing we did before. Put in more rectangles. Okay? You'll notice that the more rectangles you put in, the more of the gaps you fill in. And the more rectangles you put in, the less of an overestimate you will make. Right? So we can increase the accuracy of our approximation by just increasing the number of rectangles. So here's the kicker. We need to find the area under the curve to be the area obtained by using, how many rectangles do you think?
A lot.
A lot. An infinite number of rectangles. This allows us to fill in all the gaps, and we can get a precise area, right? Because if there's a gap, throw in more rectangles, and you have an infinite amount to throw in, and so you can fill in all the gaps, and you can find the exact area. Now, theoretically, this works because we have the tool of the limit, right? We have limits, and we can take them to infinity. So I can create a function that's going to measure these guys, and let the variable in that function go off to infinity, and that's theoretically equivalent to using an infinite number of rectangles. Not something we can do in actuality, but in theory, this is sound, and we can get an answer that way. I'll talk about that a bit later, but for now, let's actually do some examples. But first I want to throw in this specific notation. So here's our function f(x). Here's our a, here's our b. So let's say I'm dissecting this into n subintervals, right? So we're going to make this more general. And I can tell you how many subintervals I want, how many rectangles I want. And let's say I do it in such a way that all the subintervals are of equal length. What length would they be? So we're taking this length here, and we're dividing it into n pieces. And what is the length of this? What is the length from A to B?
B minus A.
B minus A. So like if I isolate one of these guys and I look at the length across this, that is going to be B minus A divided into n pieces. That expression we call our delta x. That is our change in x. Right? So we start with some x value here, and that's our change in x that we keep adding until we get to B, if we're using an equal number of rectangles. And we also, this is the length or the width of subintervals. And also, we cannot also number these subscripts. So since we're a term, we usually use x with some base subscripts. So the first number is x0, x0. The last one we call xn, that's going to be the last one. And we kind of number them in the middle. x1, x2, x3, all the way up to xn minus 1 and xn. So this is just introducing the notation that we're going to use. Now let's say, for example, for this rectangle, let's say I'm using the right side and I'm touching the curve. How can I find the height? Yep.
What is the point on the curve? So if you know the equation of the curve, you just plug in x.
Right. If I know f of x, I want to find the height on the curve, I just plug in the x value into the curve, into the function for the curve. It gives me the y value, which gives me the height. So the height here is going to be f of x1. And that's going to be true for all the others. It's going to be f of whatever x value. So note, f of x gives the height of the rectangles. So this is the formulation, right? I'm going to give you a curve. I'm going to ask you to use a certain number of rectangles. On a test, I usually ask you to do like 4. It's enough to know that you kind of understand the process what you're doing without being too much so that it's annoying. So I'd probably use 4, but I could ask you to use any amount in theory. And so I'll tell you how many rectangles. That determines your xn. You're going to dissect the interval under that curve into n equal pieces, and this will be the length of each piece. That is the width of your subintervals, and hence the width of your rectangles. Right? Now, if you take the x value that corresponds to whatever modality you're using, and you plug it into the function, that gives you the height of the rectangle. And therefore, if I wanted to say find the area of this rectangle, the area of the x1 rectangle, what would that be?
B minus A over N.
Yeah.
So that's 1.
Right. It'll be your f of whatever x value times the delta x. Right? And that is how I would find the area of all these rectangles. And then I just add them all up. So let's actually do that. I'm going to give you an example. And it's going to look pretty much like the problem would look on a test. Just for you to actually put this into action, and you'll see that it's actually not that bad. This problem shouldn't give you too much trouble on the test. Let's give an example. Approximate the area under y equals x squared plus using 4 subintervals. Equivalently, I could say 4 rectangles for 4 subintervals. And I have to tell you the interval I want. On the interval 1 to 5. Using 4 subintervals. And now on a test I'd ask you only one of these, but I'm going to actually illustrate all 3. right-hand endpoints. B, left-hand endpoints. C, endpoints. So there will be a problem like that. I'll probably also ask you, maybe if it's obvious, it's not really something to look at. Whether something is an overestimate or not. So let's do that in part A. Here's how it will look. I'm going to draw a picture of the graph. You probably don't have to do this unless it's required. The graph is usually not going to be that complicated. It's much more important the process that you're using. So if you look at x squared plus 1, that's just a parabola shifted up 1. And I care about the interval from 1 to 5. Now it says using 4 subintervals, so I'm going to split this interval into 4 pieces. And so now I need to find the length of each piece, so I go down. First thing I'm going to want to do is find my delta x. Remember, delta x is b minus a over n. This guy here is like your b, this guy here is your a. Left endpoint is your a, right endpoint is your b. So this is 5 minus 1 over 4. You actually get 1. So it turns out to dissect the interval from 1 to 5 into 4 equal pieces, the length of each piece should be 1, which means you take this, you add the delta x, 2, add delta x, you get 3, and 4. So that's how you label it. Right? So that's the first thing. You want to figure out how these intervals are labeled. Right, so that tells you that you're labeling this guy 1, 2, 3, 4, 5. Now, in the case of the right-hand method, I'm letting the right side of each of these intervals touch the plate. So that's what the picture looks like. You can kind of already tell it's going to be an overestimate. It's kind of obvious here. Not always it's going to be so obvious. And so this would mean the error is going to be approximately equal to, I'm going to call the notation here R little 4 for the right-hand rule with 4 subintervals, which is going to be essentially delta x times what are the f values I'm going to care about?
2, 3, 4.
Right. So we want to measure the height of these rectangles using the right side. So on each interval, I'm going to take the right number, and that's the height. The right number, that's the height. The right number, that's the height. So I take all the numbers that are on the right of any of the intervals. Ends up being 2, 3, 4, and 5. Let's f of 2, let's f of 3, let's f of 4, let's f of 5. And so this is going to be 1 times, and then I'm just going to plug in all these y values. 2 squared plus 1, 3 squared plus 1, 4 squared plus 1, 5 squared plus 1. And that's going to be your approximation for the error. What is that? Is that a nice number? What was that?
58.
Huh?
It's 58.
58?
It's not.
58.
Put my money up for honestly.
Always believe in yourself. Yeah, so 58 squared units for whatever units the axes are measured in. That's what we're going to assume is the approximation of that area. So that's sort of the idea, right? I'll give you a function. I'll give you the interval. I'll tell you how many pieces I want you to break that interval up into. So you pretty much write that interval with the endpoints, break it up into that many pieces, and figure out the internal numbers. You can figure that out by finding the delta x, and then you just take the delta x added to each number to get the next number, and that brings you to this. Now, depending on if you're doing right hand, left hand, or whatever, you're going to take the numbers that you need to take. So in this case, we took all the numbers that are on the right sides of the intervals. And we plug all these numbers into our function that gives us the height of each rectangle, and we're multiplying each of those by the width of each rectangle. And so this is the approximation. Here we have an over sum. I'll show you how to figure that out in the non-obvious case when we have an overestimate. But here clearly we have an overestimate.
Ron,
Yeah.
what part of this requires calculus? Like I feel like we didn't use like any of the other stuff.
Oh, we're not there yet.
Yeah, I was gonna say.
This is kind of this is equivalent to someone showing you how to find the slope of a line, and you're like, what does that have to do with calculus? But really, what we're doing is we're taking an idea and we're building on that. So when you take the slope of a line and then you start putting in limits and all that stuff and make this formula, that's where the calculus arises. So I'm sort of showing you where the calculus we will be doing is coming from. It's really trying to streamline this process. Right? So here we're adding up a finite number of rectangles. That doesn't require calculus, it's arithmetic. But when you throw in an infinite number, now you have limits, now you have other stuff to worry about. And that's where the calculus comes in. But I want you to understand the basic idea of where it's coming from. And then we'll do something pretty cool, which I don't know if we'll get to today. But so same idea. We're going to do delta x. We're going to need to draw the picture. Equals b minus a over n. We're pretending that this was the question and it told me to use the left-hand endpoints. So here I would have 5 minus 1 over 4 plus 1. So this means my interval breaks up like this, where I take this and plus 1 gives me 2, plus 1 gives me 3, plus 1 gives me 4, and of course plus 1 gives me 5, where this plus 1 is your delta x that I keep adding. So that gives me the interval that I care about. And so now knowing that I need the left, I want to use the left-hand rule. I take all the left sides. And so my error is going to be approximately equal to this guy, which I know is going to be delta x times f of 1, f of 2, f of 3, f of 4. I'm going to take all the left sides of the intervals. Delta x in this case is 1. F of 1 is going to be 1 squared plus 1. Remember, f of this I'm just plugging into the function. This is our f of x. That's 2 squared plus 1 plus 3 squared plus 1 plus 4 squared plus 1. Okay. What's that one? 34. 34? typically a smaller size than we got last time, but it's an approximation. We don't care about it being exact. I mean, you're not going to get 2 exact with 4 rectangles, to be honest. The only way something like 4 rectangles would give you the answer is like you have a horizontal function. So that's the approximation by the left-hand rule. Based on the picture, we know this would be an underestimate. Let's not worry about that now, but that would be the left hand. Midpoint, same thing in principle, except you have one little extra step, finding the middle of the intervals. So in the midpoint case, again, you go through that whole thing, your delta x is still going to be b minus a over n. 5 minus 1 over 4 equals 1. So that tells you your interval from 1 to 5 splits into 4 pieces, where this is 2, 3, 4. But now what we do is we care about the middle of those two. We don't care about those numbers that we just wrote. We care about the numbers in between them. So we want this guy, this guy. So how do I find that number? I mean, it should be obvious what it is here, but how would you do the case here?
2 plus 1 divided by 2.
Right, you find the average. So you do 1 plus 2 all over 2, you get 1.5. You get 3 over 2, which is 1.5. I think you guys already guessing this number. But sure, yeah, so now this is 1.5. Once you find that first number, again, you're adding delta x to get to the next number, and delta x to get to the next number, and delta x to get to the next number. Right? So that would be, this would be the 1.5, you add 1, you get 2.5, add 1, you get 3.5, add 1, you get 4.5. And so now those blue numbers are the numbers that I care about adding. And so my area will be approximately M4, which is delta x times 1.5 plus 2.5 plus 3.5 plus 1 times 1.5 squared plus 1 plus 2.5 squared plus 1 plus 3.5 squared plus 1 plus 4.5 squared plus 1. And that is correct. So that's the idea, and that's how you complete the problem. At least one part of the problem. We'll learn more to deal with this kind of problem by the time we get to the last test. So, don't forget the point. We're going to start bringing some calculus in now. Recall, you define the area using an infinite number of rectangles. So we can always get an approximation by using n rectangles, by using, say, f of x1 times delta x plus f of x2 times delta x plus all the way down to f of xn delta x. Right? So this is an approximation using n subintervals. By the way, this has a name. So this thing here is called a Riemann Sum, named after a mathematician named Riemann, very influential, has a lot to do with the calculus that we're doing today. It's called a Riemann Sum. And so now, basically what we want to say is that the area is defined to be, we take the limit, and now here's where calculus is coming in, of this Riemann sum, right? Imagine that we let the number of subintervals go off to infinity. We keep dissecting into more and more rectangles. And that's how we define the area. So it's basically the area under a curve. We conceptualize it in mathematics according to the machinery that this guy came up with as an infinite limit of a Riemann sum. Limit at infinity of a Riemann sum. And this, by the way, has a notation. So here's the notation that we use. We use an S, an elongated S for sum. We put the endpoints of our intervals on this from A to B, and we write the function that we're using, f of x dx. Dx means with respect to delta x, so that's your dx, but this is the notation. And we call this the definite integral of f of x from A to B. So we can approximate these guys using a finite number of rectangles. We want to get to the exact area, we end up taking the limit of these guys. These guys that we're just making up, they were called Riemann sums. And once I take a limit at infinity of a Riemann sum to theoretically approach an infinite number of rectangles, I obtain what we call the integral. This symbol just means the area under the graph f from A to B, and that is our area. And it is called an integral, a definite integral. We also have, by the way, indefinite integrals. Which we just write as this guy, without specifying the numbers. And we'll discuss more both next time. I'm going to draw for you a very nice parallel between this and what we've been doing. That was surprising when it just came out, but now it's what calculus is about. So we'll stop there. By the way, this thing we're actually not going to do it this way. I'm just going to show you jump straight to the shortcut, because that's kind of it's a very technical thing. It's usually in a business class they don't really show you that. But in like a regular Calc 1 class, you'll actually do this part and you'll see some calculus for sure. But we'll pick up there next time. I'll have your test to get back to you, and then you can go.